We start today's lecture on physics of the atmosphere. Okay, this is our sixth lecture. Okay, this is our sixth lecture, and these are the lectures which we have discussed so far. Today is the first time we are using the PowerPoint because so far we have been just discussing the basic things, elementary things only, and mostly it were introductory. Okay, so in yesterday's lecture we started discussing about the atmospheric optical properties. If you recall, we started discussion on the optical properties of the atmosphere. We shall once again review that, whatever we discussed yesterday, for continuity. And then we shall go on to discuss about the mass of the atmosphere, the chemical composition, etc. Okay. Just tell me any time if you are not able to listen to me clearly or see my PowerPoint properly. Okay. So as I said yesterday, the Earth's atmosphere is relatively transparent to incoming solar radiation and opaque to outgoing radiation emitted by the Earth's surface. We have already discussed about this yesterday. The blocking of outgoing radiation by the atmosphere, popularly known as the greenhouse effect, keeps the Earth's surface warmer. Okay, this point also we discussed yesterday. Much of the absorption and re-emission of the outgoing radiation are due to air molecules and cloud properties and cloud droplets. Right? This also we discussed yesterday. The presence of the clouds and the aerosols, they absorb the radiation and re-emit it. Okay, and the re-emission in the long wave spectrum. Okay, long wave band, the spectrum. The radiation emitted to space by air molecules and cloud droplets provides a basis for remote sensing of the 3D distribution of temperature and various atmospheric constituents using satellites. Okay, this we had explained yesterday while discussing the satellites like geostationary satellites or the polar orbiting satellites. How do we exploit this property in trying to measure the presence or absence of different types of gases or the aerosols or the cloud microphysical parameters. Okay, this we had elaborated yesterday. We discussed yesterday. Okay, so we'll skip this. The atmosphere also scatters radiation that passes through it, giving rise to a wide range of optical effects like halo, rainbow, etc. And also the blue color of the sky is because of the scattering of the blue light, okay, by the aerosols whose sizes are smaller, okay, than the wavelength of the blue light, so-called the relay scattering. Okay, the blueness of the outer atmosphere is due to the preferential scattering of incoming shortwave solar radiation by air molecules. About 22% of the incoming solar radiation is backscattered to space without being absorbed. Okay, and we discussed about the atmospheric windows yesterday. Remember, we discussed about the atmospheric window, meaning that certain wavelength of the spectrum is transparent to some of the gases, and certain gases absorb very much to certain wavelength of radiation. Okay, the backscattering of radiation by clouds and aerosols has a cooling effect on climate or the Earth's surface, which opposes the greenhouse effect. Okay, the greenhouse effect leads to warming, whereas the backscattering by the aerosols and clouds can lead to cooling, right? And so it opposes greenhouse warming. And I mentioned yesterday that the cloud climate feedback is one of the most uncertain parameter or unknown things still in the cloud climate system, in the Earth system modeling system. Okay, we do not know yet clearly that whether the clouds will have a positive feedback to the climate or a negative feedback to the climate. Okay, it's a complex thing. Still, people are writing many papers and doing research on this topic. Okay, next we shall discuss about the mass of the atmosphere. Am I audible clearly to all of you?
Yes, sir.
Yes,
Good,
sir.
very good, very good. So at any point on Earth's surface, the atmosphere exerts a downward force on the underlying surface due to the Earth's gravitational attraction, right? You know that atmosphere is composed of gases, that means it is a fluid, right? And the fluid has a mass, always a fluid has a mass. And mass will always have effect by the gravitational force of the Earth, right? So, because of that, the atmosphere exerts a downward force, okay, on the Earth's surface. The downward force, that is the weight of a unit volume of air with density rho, is given by F is equal to rho g, right? Where F is the downward force. Let me try to use the pointer, laser pointer, okay? So, this is the downward force exerted by the air column of density rho, and this is given by rho times g. Okay, force is equal to mass into acceleration. That is the Newton's law. You remember the Newton's law? Yes or
Yes, sir.
no? Good,
Yes, sir.
good,
Yes, sir.
good, very good. So force is equal to mass into acceleration. Which law of motion is this? Whether it is the first law of motion
Second
or
law, sir.
good, very good.
Second.
Yes, exactly. And this is a very important law, Newton's law of motion. The entire atmospheric processes, the atmospheric dynamics is governed by this Newton's law, right? You will be studying also this in the dynamic meteorology class. Okay. The whole equations of motions that we derive for the atmospheric dynamics in the dynamic meteorology is based upon the Newton's law of motion. Okay. And so Newton's laws of motion and Newton's law of gravitation plays a very important role in the entire dynamics and physics of the atmosphere. Okay, so this is the downward force. Okay, exerted by unit column or unit volume of the air onto the Earth's surface. Now integrating this equation, let's say this equation is 1. Integrating this equation from the bottom, that is the Earth's surface, to the top of the atmosphere. We integrate this equation from bottom to top of the atmosphere. We obtain the atmospheric pressure on the Earth's surface denoted by PS. PS is the pressure at the surface of the Earth due to the weight per unit area of the air in the overlying column. Okay, so this is given by PS is equal to integral from 0 to infinity. That is almost like considering the top of the atmosphere to the infinite level. Although we know that we can't go to infinite levels, so somewhere we have to cut down or stop. But theoretically, the total pressure exerted by the atmosphere on Earth's surface is the integral of the rho g dz. Rho g dz. Okay, the rho is the density, g is the gravitational acceleration due to gravity, and dz is the depth of the atmospheric column. Now, ignoring the variation of g with latitude, neglecting the small variation of g, acceleration due to gravity, with latitude and longitude as well as height, setting it equal to its mean value, let's say g0, acceleration due to gravity is 9.807 meter per second square. Setting this value of g, this equation can be written as PS is equal to mg0. Okay, where PS is the surface pressure of the air of the atmosphere equal to m, the mass of the atmosphere, times g0, where this is the average value of gravitational force or acceleration due to gravity, and m is basically denoted as this integral from 0 to infinity. Can you see this equation or something is hiding it? Is this equation visible to you clearly?
So no, sir, that dialog box is hiding itself.
And I have to hide this box. Okay, is this visible now?
Okay, sir.
Is this okay? Okay.
Yes,
So
sir.
M, yeah, M is the basically integral from 0 to infinity rho dz. Okay, it indicates the mass of the atmosphere. Is a vertically integrated mass per unit area of the overlying air. Okay. So there was the mass of the atmosphere, how to calculate the mass of the atmosphere and how to calculate the pressures, atmospheric pressure at the Earth's surface. Next, we discuss about the chemical composition. Chemical composition. Some of you might have studied about the chemical composition already in your BSc about the what are the chemical constituents of the atmosphere. Also, maybe in one of these courses, has some teacher discuss about this chemical composition of the atmosphere in this course, in this MSc so far? Yes or no?
Yes, sir.
Yes. Okay. Good. Which subject? In which subject?
Uh, so fundamentals of atmospheric science.
Earth system sciences. Yeah.
Yes, sir.
Okay. Dr. Chinmay. Yeah.
Yes, sir.
Good. Good. Very good. So you already know about it. Some of the students might have studied during the BSc also. Like I think, what was his name? Mahapatra. What is his name? क्या नाम है उसका पूरा? Forgot his name. Devashish Mahapatra. I think he has studied a paper in. Yeah. Is he there today? Devashish, are you there?
No,
Today
sir,
So
he's
he's not.
absent.
he is
He's
absent.
absent.
Yeah, he is absent today. So some of you might have studied also this in the BSc. But anyway, we shall discuss this once again today just for continuity and refreshing your memory. Okay. So atmosphere, as you know, is composed of a mixture of gases as shown in the table, this table. Okay. Keep my watch on. Okay. Already I've taken. All right. So as you can see, it shows major gases constituents of the atmosphere up to an altitude of 105 kilometer with respect to dry air. Okay, this table indicates all the different constituents of the gases. So as you can see, and as you know, that the major component of the gas or the dominant gas in the atmosphere is the nitrogen, right, which constitutes of almost 78%, right? Then it is followed by oxygen, which is about 20%, 21%, 20.95. Okay. And then rest are the trace gases. Next in the line is argon. Okay, 0.93%. Water vapor is also there, and water vapor, although it is existing in such a small quantity, only 0 to 5%. I mean, it can be zero also in a very dry situation, dry atmosphere, right? But it is a water vapor because of which the entire gimmick of the weather systems, right, occurs in the Earth's atmosphere. If there was no water vapor, then nothing would have happened, like no cloud would have happened, no rainfall would have happened, nothing. So this very small quantity of water vapor leads to so many varieties of atmospheric phenomena that we see in the sky and encounter, experience day to day. Okay, carbon dioxide, although not very high, but it's very important. All these highlighted gases are actually the greenhouse gases. Their presence in the atmosphere, if the quantity increases, then that can lead to greenhouse gases, strengthening of the greenhouse gases, which can lead to the global warming, right? So people are very careful and they talk about reduction of these gases, right? Carbon dioxide, methane, etc., etc. Okay, and so on. Ozone is such a small quantity, but it is so important at the same time. Okay, as you will see, majority of the ozone exists in the ozonosphere or stratosphere, but its presence is so crucial that if it was not there, as you know, that, then it would have been difficult for us to survive on the Earth, right? Because it filters out the or absorbs the ultraviolet radiation, which is so dangerous. Okay, so the nitrogen and oxygen are dominant constituents. Okay, as we discussed. Argon is present in much higher concentration than the other noble gases like neon, helium, krypton, and xenon. Water vapor accounts for roughly 0.25% of the mass of the atmosphere. Such a small quantity, as I said, but so important, right? Because the whole atmospheric weather systems, whether it is a cyclone or cloud, thunderstorms or whatever, rainfall, snowfall, everything, it all occurs because of the water vapor, although its quantity is so less. And this is also considered to be one of the greenhouse gases. It is a highly variable constituent, as I said. Sometimes it can be very dry, atmosphere can be very dry, maybe about 10% only humidity, and sometimes it can be very high, 100% humidity, saturation, right? The most important of all these so-called greenhouse gases are water vapor, carbon dioxide, and ozone. Trace constituents like methane, nitrous oxide, carbon monoxide, okay, CFCs, there is a chlorofluorocarbons are also significant contributors to the greenhouse effect. Although aerosols and cloud droplets account for only a minute fraction of the mass of the atmosphere, they mediate the condensation of water vapor in the atmospheric branch of the hydrological cycle. Okay, you know that for clouds to form, the water vapor has to condense, right? You will study this in more in detail later on in this class or maybe in some other subjects also in cloud physics. But for the condensation to occur, we have to have some base, some platform, some aerosols. If the atmosphere is completely clean, if the air is pure, completely clean, the condensation is very difficult to occur. And in such atmosphere, such situation which is pure and clean, it requires supersaturation, supersaturation to occur to have the condensation. Right? So if there was no aerosols, probably it would be difficult for the clouds to form. Right? So clouds, I mean, aerosols are important in that for that reason. Okay, and these are the components of the hydrological cycle. You have heard of the hydrological cycle, right? Have you heard about the hydrological cycle? Yes or
Yes, sir.
no? Okay, good. Who is that? Can you identify yourself with that?
So Deepak, sir.
Deepak. Okay, good. So you know about the hydrological cycle. Good. What about others? Have others also heard about the hydrological cycle? Hmm? Yes or no?
Sir, is it the water cycle?
Yeah, water cycle. Yes, in some form it is basically water cycle. Anybody else?
No, sir.
No, you have not heard about the hydrological cycle. Okay, I mean this maybe you will study later on also in detail. But Deepak, can you just say what is the hydrological cycle?
Yes, sir. Sir, I don't know in depth, but the basic idea is how
Yeah.
water, how rainfall is, evaporating and becoming clouds and come back to Earth as rainfall, and in between, it is there in seas and other water bodies. So this cycle is referred to as hydrological cycle, sir.
Yeah, precisely. Actually, this is what is the basic meaning of the hydrological cycle. I mean, generally, it is important for the hydrologists. You will study this later on in the hydrometeorology course in detail. But essential idea is that it is the cycling of the water in the atmosphere. Like just now Deepak said, he mentioned that the water bodies which are present on the earth's surface, like ocean, like the ponds, like the rivers, like the lakes, right? So all the water bodies, they get evaporated. Evaporation takes place or occurs from the water bodies, and the water vapor which is evaporated, that goes into the atmosphere, right? And as it rises up, it forms the cloud, right? Condensation occurs. As it goes up, it cools down, and the condensation occurs, clouds form, and when the clouds grow deeper and deeper because of so many cloud microphysical processes that we shall study later on in detail.
Sir,
Yes,
so this is called a water cycle also, no, sir?
yeah, it can be called as water cycle, but hydrological cycle is more popular. It's more known
Okay, sir.
conventionally as the hydrological cycle, right? And
Yes, sir.
so, yeah, who is that? Is that Varsa or Krishna? Who said? just now? Who spoke? I'm
Sir,
not able to
Sri Lakshmi.
Sri Lakshmi. Okay, I'm not able to see your face because my screen is fully covered by the PowerPoint. Okay. Gradually, when we interact more, I will start recognizing your voice. Okay. Right now, I don't recognize your voice yet. All right. So Sri Lakshmi, good. So eventually, when the clouds grow deeper, the precipitation occurs, the rainfall occurs, and through that, again, the water vapor or rain, or the water comes down to the earth. And this is a cycle. The cycle goes on, right? Always, this continuous process. So this is called the hydrological cycle or seaside water cycle, right? So that means that the total water vapor or the total water in the Earth's atmosphere system is always conserved. The total water vapor in the Earth atmospheric system always remains conserved. This is very important integral property of the atmosphere, right? This is called also the conservation of water vapor. That means if you integrate the water vapor from bottom to the top of the atmosphere and from east to west throughout the globe, then the total water vapor must remain conserved. Just imagine if it was not conserved, what would have happened? Suppose if the water vapor does not remain conserved, that means water is escaping out of the atmosphere somewhere to the space. Just imagine if the water vapor was not conserved globally. I'm talking in the global sense, not in the regional sense, not our India, or not our any country, but in the global sense. The integral water vapor integrated from bottom to the top of the atmosphere throughout the globe must remain conserved. If it does not conserve, that means it is escaping somewhere to the outer space. And if that continues, then we will start losing the water vapor from the Earth's surface. And we will become like, some of the planets which people are still trying to probe whether there is water or not. For decades and decades now, we are still trying to probe whether there is a water on the moon surface or the marital Mars surface, right? And we become very happy, if some rocket satellites, space probe finds a trace of water vapor in the moon or the Mars, then we start talking that, oh, there is a water vapor, trace of water vapor or water found on the Mars. Because no, this is so crucial, so important for the existence of the life, right? Water. Without water, no life would have existed, right? So just imagine if water vapor was not conserved globally, then it would have escaped and our Earth would have become like a Mars or Jupiter, maybe, in terms of the dryness, right? So it's so important. Hydrological cycle, right? It is recycle between Earth and atmospheric system. Okay. But that is the nature, right? That is the nature. And when we try to model them by writing through mathematical equations, now later you will study about the modeling of the atmospheric processes or NWP, that is the numerical weather prediction. You will study that in the model because everything is approximated, because still we are far from understanding the nature in a perfect way. So things are approximated. Therefore, models, when we develop mathematical models, including all dynamics of the atmosphere, all physics of the atmosphere, still the model is not perfect, right? And so, as a result, what can happen is that in the model atmosphere is likely sometimes that the water vapor is not conserved in the model atmosphere, right? Mind you, that two things we are talking. One is the real atmosphere, another is the model atmosphere, right? So in the real atmosphere, we know that water vapor must be conserved. But when we are writing mathematical models, it's likely that because of our imperfect understanding of the physical processes or dynamical processes, the water vapor is not conserved. And in such case, in such models, there will be always a problem, right? So when we develop a model of the atmosphere, we have to keep these things in mind. There are certain integral properties of the atmosphere that must be obeyed or conserved all the time. Then only the model will be perfect. Otherwise, the model cannot be perfect. It will give you a junk result when you integrate the model for a future state. Because all these models we developed to find out the future state of the atmosphere, what will happen after, say, 3 days from now, 5 days from now, 10 days from now, 1 month from now, 6 months from now, 1 year from now, 10 years from now, or 50 years from now, to know about the climate scale, right? So all these things we talked about, the people talk about the climate change, etc., blah blah blah. What is the basis of that? People talk about now after 50 years, this will happen to the climate. Global warming will take place, rainfall will reduce, or severe weather systems will become more severe. Blah blah blah. All these things they talk about. What is the basis of that? How do they know that this will happen? All that they know is through the modeling, through our knowledge of the atmospheric dynamics and atmospheric physics, right? So for weather forecasting, when we are making a weather forecast for next 7 days, or next 10 days, or next 15 days, we call the numerical weather prediction, NWP. There also we have to use the model. And the same model with little modifications, we also integrate that to seasonal scale or to the climate scale for integrating it to several years, right? So this is a whole fundamental aspects of the modeling of the atmospheric processes based upon the knowledge of the atmospheric dynamics and atmospheric physics. Okay. Now going ahead, they participate in and serve as the sites for important chemical reactions. That means all these constituent gases. And they give rise to electrical charges, separation, and a variety of atmospheric optical effects, right? All these phenomena that you observe or experience in the atmosphere, like formation of the deep clouds, cumulonimbus clouds, right? Lightning, thunder, etc., etc. All that is because of the presence of the water vapor. Had there been no water vapor, there would have been no charges separation in the clouds. There would have been no lightning, no thunder, no rainfall, etc. So this is the whole basis of the entire atmospheric processes phenomena. And just imagine, its quantity is so small, right? Its quantity in the atmosphere is so small, hardly 0 to 5%, varying so much across the earth. So I think that about the chemical composition. Probably is already time is up today, so we will stop here and we will continue in the next class about the vertical structure of the atmosphere, right? So is that okay? So I will stop sharing my presentation. Okay, and I see that about 13 students are there only. So is there any point to discuss on whatever we have talked today? Do you have any questions? Everybody is silent. Am I audible to you?
Sir.
Yes, sir.
No, sir.
Okay. I'm audible and visible clearly, right?
Hello, sir.
Yes, sir.
Sir,
Yes, sir.
Yeah, who is saying something?
sir, is
Vijay.
water vapor is aerosol or not, sir?
Water vapor is aerosol or not? Water vapor is considered as a form of gaseous substance, right?
Achha.
Whereas aerosol is like a solid substance, hanging particles, like sand particles, right? So that way you can imagine, right?
Okay.
When
Thank
I
you.
say that we have to have an aerosol in order for the condensation to take place. That means because, as I said already, that condensation cannot take place so easily unless there is a presence of aerosol. Again, too much of aerosol is also not good for us. Right? Like nowadays, Delhi is so polluted, people say. And in fact, also Delhi is very much polluted. But that is because of the presence of so many other substances, right? Smokes, age, and many other particulate matters, right? Those are not good, and anything in excess is not good. Anything beyond a certain threshold value is not good, right? So if it becomes too much, we start getting breathing problem. No, we start developing asthmatic disease. So too much is always bad, right? But in certain small quantities we have to have for the processes to go on, right? All those things we shall study later on in detail. Okay.
Okay, sir.
So today's PowerPoint and then quality of the voice and quality of the video, were they all clear?
Yes,
Yes,
sir.
or no?
Yes, sir.
Yes, sir.
Yes, sir.
Good, good, very good. So now it's all recorded, and as I say, now I will start. I will stop recording, and then let's see who has got this recorded video. Okay, I will get the recorded video today. So stop recording.